Welcome everyone to the second day of the joint USA-Chile workshop on hyperbolic geometry. This is organized by our research center, Geometry at the Frontier, and it's part of this event. It's part of the activities of a collaboration project between CUNY in the United States, City University of New York, and Universidad de la Frontera in Temuco, Chile. It is my great pleasure to present Dragomir Saric, or okay, let's say Saric or something like that, or Saric.
Saric.
Yeah, from City Saric. Okay, very good. I thought so. From the City University of New York, who will present his talk called Detecting Ergodicity of the Geodesic Flow on Infinite Hyperbolic Surfaces via the Fenchel-Nielsen coordinates. Dragomir, go on.
Thank you very much. Thank you for inviting me. It's a pleasure to be, this is my first joint USA-Chile workshop or conference. I'm sure there were some others in the past, and then there'll be more in the future. It's a pleasure to be here. I really like the picture, the picture on the conference poster. So maybe one day I can be there as well. So what I'm going to say here is a joint work with Ara Basmejian and Hrant Hakobian. So I'm going to start by, so unless we say differently, all surfaces will be infinite, which means Frontal group is infinitely generated. And in that case, without much mentioning, we know that surfaces have hyperbolic metrics. So this is a workshop on hyperbolic geometry, so that fits in. And usually, I will think of surface X as quotient of the upper half plane by a Fuchsian group. And when I talk about any metric properties, they will be with respect to this hyperbolic metric. So we're interested in geodesic flow, which is a map from R times the unit tangent bundle of X into unit tangent bundle of X. And if you're given a vector V, unit tangent vector V, and if you are given T, then the image of G of TV is given by flowing along the geodesic, which is tangent to the vector V, the length T, and then taking the unit tangent vector of this geodesic. So we're interested in this flow, and to study this flow, first we have a measure which is invariant on this flow. This measure is called the Lingual Measure. So you can start by defining Lingual Measure on the unit tangent bundle of the upper half plane, where then the Lingual Measure is given as dx dy over y squared. That's the regular hyperbolic metric on the upper half plane, times dt, where t is the angle in the tangent plane. So L is invariant under the geodesic flow and under the action of PSL2R. Because of that, when you quotient out the upper half plane with the Fuchsian group G, you will get a measure on the unit tangent bundle of surface X, where X is equal to H mod G. And the question that we will mostly be interested in is when is the geodesic flow is ergodic? And geodesic, so for infinite surfaces, this measure is infinite measure. So ergodic in that setting means that if you have any invariant set for the geodesic flow, then its Lingual measure is either 0 or Lingual measure of its complement is 0. Okay, so in the case of finite Riemann surfaces, which are hyperbolic, the question when geodesic flow is ergodic is well known and kind of classical. So if our surface is either compact or has punctures, then which is equivalent to saying that the area is finite, then geodesic flow is ergodic. And if the area is infinite, in which case that means that we have these funnels attached to the surface, then the geodesic flow is not ergodic. So this is also kind of very well known and studied. So now in the case of infinite surfaces, we have also a lot of work has been done. There is this famous Hop-Tsuji-Sullivan theorem, and then to that I would like to add Bishop and Nastal-Zinsmeister conditions. So if you start with an infinite Riemann surface, which is given as H mod Fuchsian group gamma, then the following are equivalent. So the geodesic flow is ergodic. The Poincare series diverges. So that means Poincare series is the sum over elements of the group of e to the hyperbolic distance between a fixed point z and image on the elements of the group of this point z. So if this Poincare series is infinite, that's equivalent to being ergodic. Then you can talk about Brownian motion, and you can say that that's equivalent for Brownian motion to be recurrent on X. And then the fourth property is the property which is jointly proved, or one direction is proved by Astala, Zinsmeister, and the other by Bishop. So this fourth property says that if you take a quasi-conformal deformation of the group G, then the limit set is either a circle or it has Hausdorff dimension bigger than 1. So these are all equivalent properties. And there are quite a few more of them. But this notion of ergodicity is also related to the previous work of Alford, Sario, and the whole this Finnish school, and also to Poincare was looking at this Poincare series. So they have this other additional properties. Sorry. So and the first property is that X does not support a Green's function. In that case, in geometric function theory, then X is called a parabolic surface. The next property is that the boundary of X has harmonic measure 0. And the next property is that the extremal distance between a compact subsurface of X and points at infinity is infinite. So it takes infinitely long to reach the points at infinity. So the Brownian motion will come back. It's going to be recurrent. I will say more about definition what is extremal distance later. And this is related to solving the Dirichlet problem. And this is also related to solving the Dirichlet problem as well. And there are many other kind of equivalent nice properties of this surface. Of surfaces which have ergodic geodesic flow, or we will call them from now on parabolic type or parabolic surfaces. So classification problem is, that's the problem that we'll be concerned with. It's to basically decide some explicitly given surface is of parabolic type or not, or when the geodesic flow is ergodic. And there is really nice result by Alfors and Sario in the case when the surface is maybe a Riemann sphere minus a compact set. So when the surface is planar, so if the surface is planar, then this surface is parabolic if and only if capacity of this complementary set E is 0. And that's a very nice geometric function theory result. So another thing which after that, what people did is they looked at the surfaces which are not planar, and they looked at the Dirichlet fundamental polygon for Fuchsian group G in the unit disk, and they looked at the hyperbolic area of the part of the fundamental polygon which intersects disk of radius r, where r is less than 1. And then if this intersection is big, if it's of order c over 1 minus r, when r goes to 1, that goes to infinity at linear rate, then X is not parabolic. Somehow, if you look at this fundamental polygon and when you go to infinity, this fundamental polygon opens up more and more. It has more and more area. Then the surface is definitely not parabolic. And in the other direction, if this fundamental polygon is small enough, if this area is less than c times log of 1 over 1 minus r, then X is parabolic. But there is a lot of space in between these two conditions. And actually, Nichols, not only that, but actually Nichols proved that you cannot have a complete characterization of being parabolic or not in terms of this function, in terms of the function of hyperbolic area of the intersection, the disk of radius r. He actually established, he found an infinite convex polygon and two groups whose fundamental polygon is the same polygon P, such that quotient of one is parabolic and quotient of the other is not parabolic. So this kind of idea does not work, and sort of does work fully. It has very nice properties, but does work fully. And then sort of the reason is that when you look at fundamental polygon, you kind of don't take into account how the edges, this function here doesn't take into account how the edges are glued to each other. So that information is lost, and then you cannot have complete characterization. So additionally, Fernandez and Rodriguez have even more in this direction, but I guess we don't have to go in such detail here. Since this is a hyperbolic geometry workshop, I have to talk about pairs of pans. So a pair of pans is a topological surface which is equal to sphere minus 3 disks, and then a geodesic pair of pans is a topological pair of pans which is equipped with hyperbolic metric, and the boundary curves are closed geodesics, or maybe they are cusps. So so I have a result with Arabas median, sort of preliminary to this, which says that if you have a G group which is of the first kind, so the quotient of the Fuchsian group G by the say unit disk does not have sort of funnels and open ends like that, then any topological Pans decomposition can be straightened to a geodesic Pans decomposition. So, however, just a word of warning is that, so I guess in terms of our deciding what is a parabolic surface or not, if G is not of the first kind, then the quotient of the unit disk by G, which is our surface X, cannot be parabolic, just because if it's not of the first kind, then G will contain a big opening, and the geodesic flow can escape. It won't be ergodic. Okay, so so that's what we have. So though going back to the pairs of pans, so for, I guess, before talking about going back to pairs of pans, so for that reason we don't care about groups which are not of the first kind. So we are just interested in understanding groups of the first kind. By going back to this idea of pairs of pans, we have two geodesic pairs of pans of the same, where one cuff has the same length. This is a geodesic. Then we can glue them by isometry, and the data of gluing that is needed to completely understand the gluing is called the twist, and that's basically the distance. So if we take orthogonal geodesic between two cuffs here, and orthogonal geodesic between two cuffs here, and then you can kind of see the relative distance between this point and the glued point here, and that's what is called a twist. And I will normalize to be between -1/2 and 1/2. And then a basic sort of structural theorem due to Alvarez and Rodriguez, and in some other form to Basmejian and myself, is that every infinite hyperbolic surface can be obtained by gluing countably many geodesic pairs of pans in this fashion. And then you have to add funnels, which are these things which are already drawing in the previous picture, and half planes. Half planes, we mean, it means really like in the unit disk, you take a hyperbolic geodesic, and half plane is this part here. So it has a big opening here. So those are the two things that you may have to add, and you can get any hyperbolic surface of with this construction. So for us, that's kind of a way to think about hyperbolic surfaces as being constructed in this way. And then, as I mentioned before, we don't care about surfaces which have half planes and funnels, because that's where we know immediately that surface is not parabolic. Okay, so all this thing that I said is actually encoded into Fenchel-Nielsen coordinates. So once you have Pans decomposition alpha n, you have the length of the cuffs alpha n, and you have the twist on every cuff t of alpha n, and then for every cuff of a Pans decomposition, you have a pair of lengths and twists, and the surface is uniquely determined by these pairs of lengths and twists. And conversely, if you are given this data, then you can construct the surface in obvious way by gluing the pairs of pans based on the size and on the twist. The only thing is that this surface may not be complete. And the first example and first person that realized that is Arabas Median. So he was looking at this construction. You would take a pair of pans, and then you glue it to a next pair of pans, and you glue it to a next pair of pans, and keep gluing like that. But then if you take these cuffs to have larger and larger length here, so what is happening is that this distance along here is not going to infinity. So even if you glue infinitely many cuffs, you will kind of end up having some finite limiting point here in the sense of metric completion. And then he understood that this metric completion that you get is actually open geodesic, and then you have to add a half plane, a geodesic half plane to make this surface complete, and to have the same topology and that same metric. And the metric, the original metric on the pair of pans here will correspond to the uniformization of this completed surface. So that's why he has to add a geodesic half plane. So so when you look at this picture and you think about our goal to find parabolic surfaces, then you may say, well, okay, if I have this situation and if my length of cuffs is very large, then I will always end up in this kind of situation. Then I will always know that this surface is not parabolic. However, that's not the case. So in the same kind of preliminary work to this one, we actually showed that no matter how big cuffs you take, you can always choose twists in a clever way such that the surface that you obtain does not have a half plane ending. So the surface, or maybe the Fuchsian group, will be of the first kind. So that's true. So even if you take these cuffs to be super exponential, they will still, you can still do good twists and to make the surface complete. So this having large cuff lengths is not really obstruction in being parabolic. So that's the kind of preliminary observation. So now I'm going to give you our main theorems that we proved here, and I'm going to start with the Loch Ness monster, so everybody knows what that is, right? So it's so we have a head, and we have this genus here. So and it keeps going like that. Okay, so that's the Loch Ness monster, surface of infinite genus with one topological end. And then in this situation, what we can do is we can take these closed curves here and call their lengths L1, L2, L3, L4, L5, and so on. And then we can take these closed curves here, which cut off the genus part, and call their lengths F1, F2, F3, F4, and so on. So in this situation, so if we know that that these lengths F are bounded above by some positive constant, and if you know that the sum of these things which are cutting off the surface into finite part and infinite part, e to the minus length over 2 is infinite, sum over all, and then we can conclude that X is parabolic, or in other words, that geodesic flow is ergodic. So that's basically, so that's the type and the flavor of our results. So we have this cuff, we have this conditional cuff lengths alone, which guarantee that the surface is parabolic. And this is quite explicit because we don't have to look at the group, we don't have to take into account the whole group like in Poincaré series condition being divergent. We actually take this geodesic, which you really well understand from the Pan's decomposition, and look at the length, and then we can compute that, and we can guarantee that this infinite surface is parabolic. So in particular, this infinite surface is also complete because non-complete is not parabolic. So a particular example of this one also is a Basmagian fluid surface where you have where this F, they become zero length, so they become punctures. So it looks like this, right? Something like this, right? So in that case, you don't even have to have this condition because FN's all zeros, they all punctures. Now FN's all punctures, and you only have to have the condition on these things here, L1, L2, and so on. I don't draw this thing because it takes time for me, but anyways. So so that's the type of the results that we obtain. Okay. So going forward, then we can look at what our results are saying about other surfaces. So we can talk about infinite ladder. Some people have different names, but again, I'm not gonna draw it as a ladder. I'm gonna draw it as Loch Ness monster without infinite Loch Ness monster without head. So it goes infinite genus, accumulates at two directions. So here again, what we can do is we can take these and these curves. This is L minus N, L minus N plus 1. This is F minus N. This is F minus N plus 1. And here we have Ln, Ln plus 1. And here is Fn and so on. So we have all this division where we cut off the genus, and then again, if you assume that the length is of the cutoff curves is bounded by m, then we have this kind of condition that 1 over e to the length over 2 plus e to the minus length e to the length of minus n curve over 2 is infinite. What happens is, compared to the other condition, is if you have only one end, then we would not have this one. We would have only 1 over e to the length over 2. Okay, so that's the type of the result that that we get when we have two ends. So, like for example, Maury and later on Mary Rees, they had the type of results which they say, okay, if you take a compact surface and you take a Z cover over compact surface, then this surface is parabolic, or geodesic flow is ergodic. They have this result. So our result gives their result. So if you look at yeah, so it's here. If you look at this, so you can just imagine that you have a little bit more genus here, and this really looks like a Z cover of a compact surface, right? Maybe I'm not drawing. Oh, okay, it's not good. But now, since this is infinite Z cover of a compact surface, all these Fn's, they have the same length, and all these Ln's, they have the same length. And of course, this condition is satisfied, and this condition is satisfied because you add infinitely many positive constants, so it's infinite. So this condition a little bit improves. For example, you can think of it, this condition as improving the result of Maury and Rees, because it gives you more choice in lengths, and it gives you also, when you do the Z cover, you kind of fix also not just the length, but you also fix the twist. But our result is saying you can choose lengths differently, and you can choose twists also to kind of be arbitrary there, and nothing will be affected. So you get the same result. So this kind of gives you more examples, if nothing else. Okay, so another type of surfaces that you can handle here is actually blooming Canter tree. So basically, you start with the Canter tree construction, or also Canter tree construction works for this one. And then you kind of keep adding pairs of pants, right? So I think we had a nicer picture yesterday. I think Mary was drawing nicer picture than I am. But anyway, so blooming one means just if you don't want, Cantor set is a planar surface. So if you want to have non-planar surface, you can add genus to each pair of pants, or to some pair of pants, and you can get the blooming Cantor set. So the result here that we obtain is saying that so if you have level n, so these cuffs are based on the levels, level 1, level 2, and so on. So on the level n, you have 2 to the n cuffs, or some multiple of 2 to the n cuffs. So if you impose condition that the length of each cuff at the level n is at most n over 2 to the n, then X is parabolic. So that should be contrasted with the result of McMullen, which says that, well, if all the lengths are bounded below, then X is not parabolic. So we are kind of detecting in this part where lengths are, okay, they're going to zero at certain speed, at certain rate, and then we can conclude that X is parabolic. So also we can, all these examples are just to illustrate what kind of things you can have, but we have also a general theorem and for arbitrary surface. And this general theorem we can state in the following way. So basically we have our surface. Maybe it has many ends. It doesn't matter how many ends or whatever, but basically we take exhaustion of our surface by compact sets G1, G2. G1 is this one, right? And then G2 is the whole thing, and then this is G3 and so on, right? So and you assume that these boundaries are geodesic boundaries, and you look at LNJ to be the length of so the boundary doesn't have to have a single component. The boundary can have more than one component. So J counts the number of components of the subsurface Gn. J is the counter for J is the index for the components of Gn. So if you look at this these curves alpha and J, and if you can call L and J their length. And then in addition to that, you have to have another constant here, gamma and J. That's a slight complication. So basically, if you are here, and if your Gn is here somewhere, and Gn can have more than one component, boundary components. So these are the boundary components of Gn. Then you have maybe Gn plus 1 is the one which adds is the one surface which adds this part here. Then what you need to do is you need to get a pair of pants here which shares one boundary with Gn, and then you look at the distance, orthogonal distance to these two cuffs, and you take the bigger one, and that orthogonal distance is this gamma Jn. Okay, so that's an extra parameter that we need to have in general. So for example, in this, there was this bound of Fn which was m, so that was kind of removing the need for this extra parameter. But in general, you have to have this extra parameter, and then you can form functions a and j in the following way. So if ln is bigger than some positive constant, then you can take e to the ln over 2 divided with gamma jn. So in the previous, when we don't have a gamma jn, it was just e to the ln over 2 in our sums that we had before in the theorems. But when we don't have this thing, we have to have division by gamma jn. And if this is if gamma jn is bigger than gamma 0, which is some positive number, then we can just take without gamma jn. And then if the length is going to 0, then instead of e to the ln over 2, we have to take just ln. And then, so this is some kind of function which depends of ln and gamma, L's and gammas. And then we have this type of summation in our theorem, which says that if sum of 1 over sum a and j is infinite, then x is a parabolic type. Okay, so that's the general theorem. So far we only talked about cuffs and conditions on cuffs, lengths of cuffs, but then we also have twists. So we were missing this information, and we also able to include information on twist and to get the stronger results. So the first result is again for Basmagian flute. So remember, without the twist, here we had e to the -1/2 ln. That was the condition. But if you have information about twist, or if you want to put information about twist, then you get 1/2 minus absolute value of the twist over 2. And that makes this exponent smaller. And the terms are becoming bigger, so it's easier to sum up to infinity. So we have this condition, and if this condition is satisfied, then X is parabolic. So the old condition is this one here, and here this condition works for all choices of twists. But now we added the twist here to strengthen this result, and we can kind of illustrate that thing here. So this result is stronger with a twist in, because, for example, if you take ln to be 4 log n, and if you take all the twists to be equal 1/2. So I fix all the twists to be equal 1/2. So what happens is the surface looks like this. So you have this geodesic here, and this orthogonal geodesic here. So they're exactly half of the length of, they're exactly half, relatively half the length away from each other. So this for these cusps are going up, down, and so on. So that's the type of surface that we look. So for that surface, if you look at this condition without the twists, we can see that you get this summation e to the minus, you get n to the minus 2, which is finite. So the condition fails. It doesn't mean that surface is not parabolic. It just means that our condition does not apply. However, if you put this condition, then you get here 1/4 e to the minus 1/4 ln, right? So when Tn is 1/2, you get e to minus 1/4 ln. So 4 log n will give you 1/n, and that diverges. Therefore, the surface is parabolic. So that kind of explains how this twist helps the situation. So then, sort of like once we have this thing, we were kind of saying, okay, so our ideal theorem would be to completely characterize whether the surface is parabolic, just knowing the lengths and twists. And then we start to kind of just start trying to get some special cases where we can say that completely. And the special case that we have here is when all the twists are 0. So all the twists are 0. In that case, we have that the surface is parabolic if and only if this condition without the twist is satisfied. Sum of e to the minus ln over 2 is infinite, and that's equivalent to x of ln 0 being complete, or the group being of the first kind. So in the case of 0 twist, parabolic is equivalent to be complete, and that's equivalent to this condition that we gave in terms of the divergence of a series. Okay, so we have that, but then we ask ourselves, like, how to work with other cases, and the first other case that we looked at was a half twist. So again, going to this half twist here. So what I draw here is actually half of the half twist surface. So I cut off this surface along these, right? And I get the front part maybe. So that's kind of schematically how this front part is. These are pentagons, right? These are pentagons. So and then we have a condition to detect when the surface is incomplete. So we take sigma n is the alternating sum of the lengths ln. So this is L1, L2, L3, L4, and so on, right? So sigma n is the alternating sum of the ln. So if this sum is finite, then X is incomplete surface, in particular, is not parabolic. So that should help us in understanding when the surface is not parabolic in the case of the half twist. And our theorem is not as good as in the case of the 0 twist. So we look at the half twist surface, and we cannot say immediately. So we add another condition. We add condition on ln. We require that ln, the length, is a concave sequence, which means it's just ln lives on a graph of a concave function. Okay, that's what that means. So it can increase, but it increases in the concave way. All right. So in that case, the following are equivalent: X is parabolic, X is complete, and this 1/2 condition with twist 1/2 e to the minus ln over 4 being infinite, that these are all equivalent. So in the case of the half twist surface for the Basmagian flute, this is the result that we get. So then you can write out what this condition means in different forms. That's fine. We don't have to go there. So another point of view is to say that concave cuff lengths are sort of not good for detecting flutes which are complete but not parabolic. So that's kind of conclusion. So if you have a sequence of lengths which behave nicely in some way, they're not really good in constructing complete but not parabolic surfaces. So that's kind of conclusion here. And to illustrate a bit more, this kind of phenomenon is that if we choose length in certain way, if we choose lengths to be to depend on two constants, A and B. So if we do that, so one length is A ln n plus 1 plus b ln. That's when L is when you have 2n, a positive constant, even coefficient, and when you have odd coefficient, you get A plus b times n plus 1. Then you can apply these two criteria that we have. You have criteria for being parabolic, and you have criteria for being incomplete. So when you do that, the blue thing is parabolic. The red thing going infinitely is incomplete. But in between here, we don't know. So what is happening here? Maybe, ideally, this would be surfaces which are of the first kind but not parabolic, or complete but not parabolic. But that's a question here that we don't have answer right now. So even in the case of fluid surfaces, this general problem of deciding completely seems to us very hard. So, I mean, I didn't hear any questions, but if you have questions, you can ask me now. If not, then I will go and talk about a little bit of methods, how we do this. Okay, I don't hear anything, so I'm assuming there are no questions. So basically, the way we are dealing with this condition, we're using modulus of a curve family, and I'll give you a 2-minute crash course of what is modulus of a curve family. So you start with a curve family gamma. This family is usually kind of self-intersecting, uncountable big family, and you define a allowable metric for gamma to be conformal metric for your Riemann surface, rho of z, absolute value dz squared, such that the length of each curve in this rho metric is greater or equal than 1. So those are allowable metrics. And then modulus of this curve family gamma is the rho area of your Riemann surface infimum over all allowable rho metrics. Okay, so you have that. So then we need to notion of extremal distance, and that was one of the conditions in the beginning in the theorem of Alfors and Saric. So extremal distance between two sets in some open subset of, if this is set D in your complex, in your surface X, and you have E1 and you have set E2, then extremal distance is the 1 over the modulus of the curve family which connects the two sets inside D in any way possible. So that's extremal distance, 1 over the modulus of this family. Okay, oh, sorry. So there is, so the theorem that I mentioned is by Alfors and Saric is saying that the X, that you can characterize whether X is parabolic, which is now we know it's equivalent to being a geodesic form being ergodic in terms of extremal distance. So what you do is you take a compact exhaustion of your surface by sets. So you get set K1, then you add more, you get set K2, and you add more, you get set K3, and so on. And basically what you do is you take the boundary of K1, and here is the boundary of the set Kn of your compact exhaustion, and then you look at extremal distance inside this Kn minus K1 of the curve family look at external distance of these two sets, which is the same as 1 over modulus of the curve family connecting the two sets inside Kn minus K1. So if this external distance goes to infinity, then X is parabolic. And then this thing is very hard to check. Why is it very hard to check? Well, for us, when you start building our Riemann surface using pairs of pans, it's very hard to check what is the modulus when you start building, like adding pairs of pans, how the modulus changes. That's usually very hard to find or estimate. To precisely find, that's almost impossible. To estimate, it's also very hard. But there is a simplification to this criteria. And that simplification is basically saying that what you can do instead of, so this is boundary of K1, this is boundary of Kn, but in between you have boundary of K2, boundary of K3, boundary of Kn minus 1, right? So in between. So if your curve goes from here to here in your family, it will have to cross all these other boundaries. And then what you can do is you can take a neighborhood of this boundary, which has two boundary sides, and then this curve has to go from this boundary side to this boundary side. Piece of this curve connecting boundary of K1 to the boundary of Kn has to go through this boundary curve here. So what happens then is that the external length from the boundary of K1 to the boundary of Kn is actually bigger than the external length of these pieces here. So there is the one piece here, there is the one piece here, and there is the one piece here. So the external length across is bigger than the sum of the external lengths. That's kind of natural geometric thing that you can see anywhere. And that kind of justifies also calling it external length. So, but this is much easier to check because now you are localizing your condition here. Okay, so in this picture on the surface, basically we can put some kind of colors around these geodesics. So if you want to go from this boundary to this boundary, you have to cross each of these colors, and you sum up extremal length of extremal distance from one boundary of the color to the other boundary of the color, and you require this to be infinite. If that's infinite, then the original extremal length will be infinite. So that's the idea. So how do we do the colors? Well, there is the standard color or the standard one-sided color, which is well known in hyperbolic geometry. So if this is a closed geodesic, then you have this curve, which is on the distance r of L over 2, which is given by this standard formula. And this embeds in your pair of pans, and in your surface doesn't intersect any other color. And then Maskit was some time ago, he was proving that modulus of this color or extremal distance between these two boundaries in this color is 1 over L e to the L over 2. But remember, in our formula, we have 1 over e to the L over 2. So we don't have this L. So we needed to improve that. And the idea, our geometric idea for improving that was to define something which we call a non-standard color. So what do we do? Instead of doing this standard color here, so we have a pair of pans. Here is one geodesic, here is another geodesic. So we take orthogonal arc between two geodesics, and you get to point P, and then we drop from this side and from this side two orthogonal arcs to this side here, which is also orthogonal to these two geodesics. And then we get another color, which we call the non-standard color. Okay, and our results are basically that the extremal distance between the two boundaries of this non-standard color is this same gamma that we saw before, which is actually this length here, times e to the minus L over 2. And if gamma is bounded from below, then you can just use e to the minus L over 2. We don't need gamma. Okay, so so our improvement is this missing of the factor L. But when L goes to infinity, this is a very important factor, and the fact that we are able to construct these things and that this is not in the formula kind of allows us to have this complete characterization for the twist zero surfaces. So that's a significant improvement for us. So for twist zero surface, at least we know exactly when the surface is parabolic or not. And that is thanks to this fact that we can get rid of this L here. So just another like a geometric picture. So this is our standard color. This is our non-standard color. They're not, one is not contained in the other. However, when you take this geodesic here and you start squeezing it toward becoming a puncture, then this curve here, it's becoming more and more long, and in the limit it becomes this geodesic here, which goes to the puncture, and the standard color looks like this. So now we really see that standard color is contained in the non-standard color. But in general, that's not the case, but we have it here. Okay, and then finally, we can kind of do the gluing of, this is non-standard color with a sharp point here, and this is non-standard color with sharp point here. So we can also glue two non-standard colors together. We have some kind of twist here, relative twist, and we can compute that thing as well, the extremal length between the two. So we compute the extremal length between the two boundary sides of glued non-standard colors. So in that case, we actually, our kind of most general theorem says that the extremal length for the twist parameter is 1 over the modulus of the vertical family gamma v. So that's a subfamily of the whole family of all curves connecting two sides. And the vertical family is actually the family which consists of hyperbolic geodesics orthogonal to the core geodesic. So this family does not self-intersect and does not intersect each other, and this family is easier to compute the modulus. So we have a technique for computing the modulus. What we do, is we kind of look at this non-standard color. We lift this non-standard color into the upper half plane, and then we take the log coordinates of the upper half plane. And in this log coordinates, what happens is that the geodesic is now a straight horizontal line, and this curve here, which is the same as this curve here, which has this sharp point here. Here it's not geodesic. So this curve here becomes this one here, and then here we have this non-smooth point. So basically then our method is to kind of realize that when you look at family connecting this piece here to anything in here, it can be approximated just by this vertical family here, asymptotically. We are able to asymptotically say that when length is very large, this whole family, modulus of the whole family is asymptotically up to some constant equal to the modulus of the vertical family. So that's the bulk of our work. We have a nice technique where we kind of separate the whole family into the family of curves which have width bigger than some fixed constant delta, and family of curves which have width less than some constant delta. And when you let delta goes to 0, the width of the family is going to 0. So these curves kind of degenerate and they become vertical lines, and that's our vertical family. So that's basically, those are the estimates. We have sort of some techniques in estimating this modulus. We actually construct allowable metrics which are good in some sense that we can estimate this modulus. So that was some kind of geometric estimate. Lastly, quite surprisingly, even the last computation was very dependent on how these functions f and g looks like. Where f and g, well, in this case, f is very simple; it's just a straight line. But g is lift of this non-smooth boundary of the non-standard color, and it's very much depends on the actual precise function g, and that was quite surprising for us. And also the computation in terms of integration was kind of a little bit of challenging because the integrals are kind of big, and we want to have asymptotic behavior, so we had to really write down reduce this integration to some something which looks like this or something which looks like that, and there we were able to get the asymptotics in L. And I guess those are the techniques. Thank you.
Thank you very much, Dragomir. Let us applaud Dragomir to thank him for the nice talk. It was very, very nice, very interesting. So are there questions or comments? If anyone wants to write down in the chat, we can read the questions out aloud.
Dragomir, I have a question. Yeah, so
Professor Hidalgo, go on.
So let's talk on the Loch Ness monster. So
okay.
This monster can be seen as the homology cover of many Riemann surfaces,
Okay.
compact and non-compact surfaces in general. So can you read the parabolicity or not in terms of this basic Riemann surface?
Well, I'm not sure what kind of cover you're talking about. Is it it's
The
not the
homology
abelian cover.
It's the homology, it's abelian, so it's the highest abelian cover.
Z to the
2G, for example, for a surface of G.
well, it's known by result of Rees and Mori that if it covers Z to the R, where R is bigger than 3, bigger or equal to 3, then the surface is not parabolic.
Okay.
So we can improve on that. We can have a condition which is rather complicated, because different Z to, there's not one Z to the R cover, there are many different ones, and then they geometrically look different. So, but for each of them, we can write down, we can kind of decrease the cups enough to claim that we know that's parabolic.
I see. Okay.
Thank you.
Camilo?
Okay, thank you. I try to speak English. Okay, actually, I got two questions. Okay, the first one, do you know some function group? It's mean precisely describe of the element in this function group, such that the quotient between the hyperbolic plane and the function group be a parabolic type surface, and this guy satisfies the sufficiency condition described for you and your college. And the other question is, you have example that parabolic surface such that don't satisfy the condition.
Okay, so the first question, when you say, do I know group, you mean like explicitly written down the group? Is that like I mean, we have Fenchel-Nielsen coordinates, and then there is like an algorithm to write down, but you have infinitely many generators. So for me personally, if I have Fenchel-Nielsen coordinates, I consider I know the group. I don't know how would I do better than that. For the second question, for in the case of, like, I think the surfaces, the flute or the Loch Ness monster, I think they are very interesting, because even there we don't have complete answers. So I don't have example in the case of Loch Ness monster, but I think in the case of more ends, we should be able to give an example, because I believe that our condition is close to being sharp for one end and finitely many ends, and when you have infinitely many ends, I believe it's not very close to be sharp. That's my feeling, but we don't have example for one end. For many ends, I think for Canter set probably we can find that. That shouldn't be hard. All right, thank you.
Any other question for Dragomir? I don't see more hands. Okay, so we thank Dragomir again. Thank you very much.
Thank you.